So you guys get to reap the rewards of a mistake that my wife and I made. We bought all these Middle Eastern treats for an art gallery opening that was opening tonight. But when I went to deliver them, no, it's opening a week from tonight. So they will not last. So for you. So there's baklava and then other Middle Eastern cookies. Pistachios, I believe, yes. Okay, so let's start off with, in fact, today will be about the midterm. So first off, my apologies. I did not calibrate the number of questions correctly, so as I would have wished. So I made an adjustment with an extra bonus question, which was worth some number of points. And you all got those points. Okay, so yeah, I did not intend for everyone to be working until the very last minute and many of you not being able to do some of them. So these were the distribution of raw scores out of 75. And these are the percentages. So a mean of 80, a max slightly over 100%, a low of 38. And then do you guys get to see this stuff? I'm not sure you do get to see you get to see the overall mean and things, don't you, on GradeSource? Or GradeScope? Or do you just get to see yours? Oh, well, here we go then. Here it is. So, and I guess I'll just scroll through here. Some of the questions were harder than other questions. Like this one was hardest.
Which one's that one?
That one, we'll see. We'll get to that. That was the last non-bonus question. So that was, how could you have more than 2 gig of addressable memory?
So is this the hardest, or does it mean just a lot of people didn't get to it? Or didn't get enough time on that?
Yes.
Here is my hope that you would look through the exam and sort it. Like on Amazon, I sort by low price normally. And so on an exam, sort by easiest. Well, that's not really true. Sort looking both at how easy it will be compared to the number of points it gives, right? I am always surprised. Sometimes I give bonus questions, right? And I make it the last, and it says bonus. And as I'm grading exams, the bonus question, like half the people will do, let's say. And I think to myself, the bonus question is worth just as many points as any other question. And just because it says bonus doesn't necessarily mean it's harder. And points are fungible, so you could choose to not do another problem. So anyway, let's go through the exam. All right, so here's our x86 file system. We have these various sizes. This is just the layout we looked at in class and is also right in the code and is also in the book. So, and we have just a single directory, which is the root. So the question is, what's the maximum size a file can be? Most people, I'd say, got this right? So we just look at the inode. And the question is, in the inode, how many blocks can we reference? How many direct blocks can we reference? Unfortunately, we can't tell that from here. So where would we look? Code sounds good. Let's try that. Let's see. If we're not sure where we're looking for, we could look for inode, I guess. 40162. There's our inode. This is an in-memory copy of our inode, so we might want to look at the on-disk version. But the fact is, the number of addresses is the same. So we have indirect. Oh, well, that's not so handy. So indirect. Okay, so we have 12. Okay, which actually I already knew that. But so we have 12 direct plus 1 indirect. No doubly indirect, nothing fancy like that. So the 12 direct means this is 12 blocks, right? And the 1 indirect means we go through a block and we have a bunch of entries here. How many entries here do we have? That's 512, right? Each of these is a block number, which is 4 bytes. So we're left with 512 by 4, or 128. So we have 128 plus 12 blocks at 512 bytes per block. And I was perfectly happy if you just say 140 times 512, but a lot of you multiplied it out, and that was nice. So it's around 70K. Any questions on that? Okay. Oh.
70K is the answer to every single question.
But now it forgets. I don't want to write it again, though, because, well, no, I don't want to write it because I'm afraid it'll stay. So how many such maximum size files can there be, and what is the limiting factor? What are possible limiting factors? For how many files? Yeah. Number of blocks. Yeah, how many file blocks do we actually have? Like, how big a disk is this? And it just goes on. They're a lot. So it could be a 2 gig disk, a 2 terabyte disk, a 2 petabyte, or whatever we have a new size being designed, right? Does anyone hear about that? Petabyte, exabyte, and I think there's a... Yeah, but past that, they're trying to come up with others because they start needing them. But we don't have any hard drives that big. So anyway, number of blocks is one. What's another possibility of a limiting factor? The bitmap of blocks, because this tells us what blocks can be used or not. And so anything that can't be referenced by this bitmap, we can't use. So that'll be a more limiting factor than just number of blocks. And then what else? Inodes, number of inodes. Yeah, so we're going to want to know some of these anyway. So let's look at the limit of the number of inodes. And one question is, how many inodes do we have? Well, an inode is 64 bytes. How many of them will fit into a disk block? 8 times 64 sounds about right. So we have 8 inodes per block. And how many blocks do we have? Well, from 32 to 57. So 57 minus 32 is 25, but that's not how many blocks do we have. How many do we have? 26. This is what's called the fence post problem. All right? If you have fence posts and fences, there are more fence posts than there are fences. And that's kind of the same problem here. So we have 26 blocks, inode blocks. So 26 times 8 equals 16208 inodes. So we can have at most 208 files, right?
Well, you need an inode for the root directory.
That's correct. So we got a -1 for the root directory. And so that's 207. All right, so that is one possible limiting factor. Let's look at the bitmap case as well. So the bitmap, we've got this one block of bitmap, right, where every bit represents a block. And so therefore, we have 512 bytes times 8 bits per byte equals 4096 bits. Yeah, equals 4096 blocks.
Does that start counting at sector 0, or does that start counting at sector 59?
Should be 59. Yeah, should be 59.
Okay.
So we could look at the code to see, but if I were doing it, I would make it 59, because that'd give me 59 more. Okay, so 4096 blocks, and we saw up here that we had 140 blocks. per maximum size file, right? So 4096 divided by 140 is,
29-ish.
yeah, it's around 29. Okay, so 29 is less than 207, and so
Just make them all the same file and hard link it a bunch of times.
well, so for maximum size files, we're not saying that the contents is the same, right? So, and in any case, what would that wouldn't, well, so that would save you, wouldn't it?
And you don't need to have separate storage for all of them.
Yeah. So would you need inodes? Would you need separate inodes?
No.
Yeah. This is going to be relevant when we get to part D, by the way. So we could share the same inode, and we could share the same data blocks. It's weird to do that for this large file. It's going to make a lot of sense for an empty file, because there's no way to distinguish the contents of empty files, of two different empty files, is the same, it turns out. So 29 is what we want to do here, and we'll see on D what would happen if we made them hard links. The minimum size of file, I did not realize how hard this would be. So it's just 0, right? There's a size in the inode, and it's a number of bytes, and it can be nothing. I wish I'd specified the units. That might have made it better. And then how many such minimum file size files can there be? Well, we're limited to 207 inodes, right? We're limited to 4096 blocks. How many blocks are we going to need for an empty size file? You don't need any, because the blocks are for data, right? So this won't matter. So you might say, well, it's 207. But we have to also look at, let's see, so let's look at the directory entry in the root dir. So if we look at the root dir, that's also going to be a limitation, right? How many files can you plop into a directory? And so how many files can you plop into a directory? Well, we need to know how much data there is, right? We already said that's 140 times 512 is the number of bytes that can be in a file, including a directory. And we divide that by the size of each directory entry, right? Which equals 16, I believe. And so that equals 140 times, so 512 is 2 to the 9th, 2 to the 4th, 2 to the 5th. Directory entries, okay? Minus 2, 4, dot, and dot, dot, right? That should be just 2 dots, dot, dot. So that leaves 140 times 32 minus 2 for other files. And what we can do now is hard link. So if we use a hard link for this empty file, we'll have this many references to the same inode. So we won't need to use all these 270 inodes. We'll just use one inode. That one inode, addresses will be 0. There's no blocks associated with it. The size will be 0. And the directory entry will have whatever name. We're going to have to come up with distinct names, I guess. So distinct name, inode number. Distinct name, same inode number. Distinct name, same inode number, and so on. And then if we look at the ref count of that inode, it'll be big, right? Because there are a bunch of links to it. Does that make sense? All right. And you got a lot of points if you got to the inode limitation. All right. So the simplified X86 architecture, it's a fair amount simpler in that the addresses are so much smaller. So we have our 8-bit virtual address, right? And we have 8-bit physical addresses, right? We have 256 bytes of physical memory. How do we get to the fact actually that it's 8 bit physical addresses. What tells us that? I'm going to circle two things. We got this offset, right? And the page number is going to go through the page table and come back with a page table entry and then give you this frame number. And they'll be appended together. So if this were larger, we'd have more than 8 bits of physical address. And if this was smaller, we'd have less. And those are all possibilities, although it's most common to be the same. All right. So page table, segment table. Key thing to remember about segment. Segment just tells you in some sort of an address space, in the case of x86, in a linear address space, where's the segment, right? So this segment is here, right, at 0x10. And the data segment is up here at 0xFO. And the stack is here. But the other thing we need to know, as well as where it starts, is where does it end, right? So we need to know how big it is. So this is 8 big, and the stack is 40 big, and the data segment's 10 big. So when we use a segment, like here, for the instruction pointer is going to use the code segment. We take this address, and we say, is it within bounds or out of bounds? Is it within 8 here? Yes. So it's less than or equal to 8. We're good. Second step, add the base address. So 1, check that 06 is less than 08. 2, 06 plus the base address of 10 equals 16. So 06 is a virtual address in x86 speak. What is 16? Anyone remember the naming that they use for that in x86? It's a linear address, exactly, linear. But we're not done because we want a physical address, right? So our page number is here. So that'll say go to page 1. That'll say come up with frame 3. And so we're going to replace the 1 with a 3. So 36 would be the answer, all in hex. Questions on that? If the instruction pointer were 16 instead of 06, then it's bigger than the length. So it's not in the code segment. So it's invalid. One 6 is greater than 8. And how does that show up when you're actually executing? Yeah, I don't know if they distinguish it. Yeah, we're going to get a fault. I think it's the same whether it's segmentation or page. I'm not sure. Maybe there's a separate segmentation fault.
It's a fault.
Yeah, it definitely is a fault, and it'll go to the trap handler for whatever that fault is. Any questions at this point? Okay. The stack pointer is 18, the physical address it refers to. And again, the fact that it's the stack pointer, the architecture knows what segment to use, right? So for the instruction pointer, it knows to use the code segment. For the stack pointer, it knows to use the stack segment. Yes?
None of the questions had it what pointer would access the data segment.
You're right, because we hadn't explicitly talked about that, and so I just didn't want to get in to have to try and explain it in the question. I knew you would know code and stack. But which registers use the data segment and the other segment are a little picky. So. Okay, so if the stack pointer were 18, we do the same sort of thing. Check number 1, 18 is less than 40. Number 2, 18 plus 30 equals 48. And 3, 4, 8 goes to. So 4 says we go to page 4, pull out the frame 1, and then append the offset 8. And then if it's 2, 8, again, we pass the first check. We add 2, 8 to 30, and we get 58. 58 says to go to page 5. We go to page 5, not present. So we get a page fault. Questions? Okay, moving on. Different processes. All right. So X is in this infinite loop, right? Knowing nothing else about anything, are we going to print here? No. If it does print here, something is horribly wrong with the compiler or the operating system, right? So it won't print anything. And the question is it possible for process X to execute any more user space instruction after the event completes, where the event is another process calls kill, and kill runs all the way to completion. So the kill happens. And the question is, does this guy ever run again? And the answer requires a little bit of looking. So you can imagine it could, although it'd be nice if it didn't. Okay? And what we have to really look at is what happens in trap. So in trap, well, let's break up a second. So process X, why isn't it running? How did it get to be not running?
Because process Y, because presumably there was a timer, and so then that's how process Y started running.
Okay, so there was a timer, or what's the other way you can get in the kernel? A system call, or another interrupt. Those are the three ways your user process can get in there. So we either got a timer, presumably when it was in infinite loop, or got a system call. Can that be? Well,
there aren't any system calls that it would make.
Well, keep in mind, like on JOS, we call get inv-id, right, in the library
So it could have not started.
before. So are there any system calls that the kind of glue code before it gets to your main calls? And I don't think so. We load right into our main in XV6. So I don't think we'd have a system call. You had a question? Yeah. Okay.
Oh, I was going to ask if it was possible to get interrupted from another system call that Y made.
So we're on one CPU. And so Y wasn't running when X was running. So, but it could be another interrupt, like process Y issued a disk read, and it was sleeping, and then the ID controller said, hey, the disk read is finished. It could certainly wake us, process X, up, pop us up into the kernel where we'll deal with it, and then schedule another thread to run. So interrupt, really there's only one way into the kernel. It's the trapper interrupt, which is all really the same exact mechanism, right? That's the only way in. But we break it down into system calls, interrupts, and then just various exceptions, like divide by 0 and so on. But in this case, presumably it was a timer that caused it to go in. The other possibility, I guess, is it never was running. It got scheduled to be runnable, and Y came along before we ever got a chance to run it and said, wait, no, don't run that thing, kill it. Okay. So here's the key. If we were a system call that caused us to get in here, then we would have called the system call, which might have put us to sleep, But when we return from the system call, we would see that we're killed and we'll exit. And exit is what never, has us never return.
What if we
Andy.
don't even get there? What if we die on the first kill?
So there are two things to keep in mind. One, how did we get into the kernel? How did process X get into the kernel? If it was a system call, when process X came in, it wasn't dead. It had not yet been killed, right? So it went into the syscall, and somewhere in there it yielded. And then process Y starts running. Process Y marks it as killed. Eventually X comes back and starts running again, and this is where it'll come back from. And this is where it'll look and it'll say, oh, I just got killed. But it also makes sense to check before, too. After is, what if someone killed you while you were asleep? Before, what if someone killed you while you were running and then you made a system call? What was the other possibility? We could have an interrupt, like a timer interrupt, for example. And in any case, for all these, so let's say we had a timer interrupt. This is what causes us to go to sleep, right? We got a timer interrupt, our time is up, we yield to someone else. If no one else is waiting, we get to run again. But this is not going to return for X until X gets scheduled to run again. And when X gets scheduled to run again, it wakes up from here, and it looks and it says, oh, wait, before I go ahead and go back to user land, let me just check. And it checks and it sees, oh, I have been killed. Therefore, I will exit. So the upshot of this is, no matter how we got into the kernel, we're not going back out in this one CPU case. So, no, for the reason I just described. Okay, and it's in this solution, which I'll post shortly. If we have two CPUs, it's a different story.
Sorry,
Go ahead.
just to clarify.
Yep.
I understand that it's no, but just to be explicit about it, given that we have one CPU at any given point in time, only one user process will be running.
Yeah, so guess what we can say here is, if Y is running, X isn't. And when X returns to its kernel thread, trap will check, killed, and exit.
So that's what I said, and I'm not clear on why I didn't get all the points.
That would be a great thing to talk to not in this venue. So I'm happy to talk about that, but
Okay.
okay. If you have two CPUs, then that part is not true, right? If Y is running, X isn't. Because it could be that Y is running on one CPU and X is running on another CPU. So you're Y. No, it'll be more fun. I'll be Y and you be X. You're running, I'm running. I kill you. How do I kill you? I just mark you as killed, right? So I put a big X on his shirt. But that doesn't stop him from running. He's running, right? Until when?
Something makes me go into the kernel.
What could make it go in the kernel?
Timer or a system call or...
Yeah, so if you're stupid enough to make a system call, then all of a sudden you would be exited. And so if you just wait as long as you can, eventually the timer will come in. And then we saw how the process will come about that you'll get exited. So the answer here is yes, if X and Y running simultaneously. Now, what's going to cause it to go in the kernel? Is it a system call? No, we know it's not a system call because that loop is infinite. Okay? So it will keep running forever. So it'll never get to the printf. If it somehow did have a system call in the infinite loop, then yes, the system call would cause it to exit and it'd never return. Okay, so the timer interrupt will send us into trap, which will check kill, then exit. And there's no print. And by the way, optimizing compilers, even heavily optimizing compilers, do not optimize away infinite loops. They're careful they'll make them quicker, but they're careful to leave them there because they want the same behavior. I made a mistake because when I started this morning, it actually asked me if I wanted to rate it. And I obviously made a mistake by saying no. I think it's also interesting that you just lose this, right? It just doesn't, it saves to the cloud, but it'll let us quit without, anyway.
Have you had it do that when you're not in full screen mode? Or is it only in full screen? I haven't paid any close enough attention.
I don't know. Let me make it big, but not full screen. We very rarely run in non-full screen, but let's see. Okay, kill, get PID. So we call get PID. We'll still be running. We call kill. That's a system call, right? So our code is here, a system call. We're going to call the system call. What system call are we going to call? Exit. Which procedure, which process is going to be killed? Our process. So when we go check here, we're killed. We're dead. No more. No print. No more user space instructions. So kill is a system call. After system call, trap, checks killed, and calls exit. All right, we got one more. Wait, we have two more. So our code tries to write into an address that is not in fact our own, right? It's in kernel space. So what's going to happen? If we try and use an address to which we do not have, if we try to write to an address to which we don't have write access, and even try to access something we don't have user access to, yeah, we get a page fault. So the page fault will take us into trap. And what does trap do? Don't get confused with lab 4B. It does not call an upcall handler, right? So you did something bad. It can't just return to you, printing a stern warning to your console or anything, because where would it return? The same instruction that was failing? So either we return the next instruction and say, whatever you tried to do just didn't work, but I have no way of telling you that. But sometimes your instruction just won't work. Not good. All we can do is kill you. Okay. So this goes to kill and then exit. So no. We're not going to process any more user instructions. So we had one no, two no's. We had one yes with two CPUs. So therefore, we're overdue for another yes. Okay. We open. Don't use that as a guide. So we open a file, and we read from that file. We read 5 bytes from the file. And I was careful to say the file is of link 10, so there's no problem of running out of end of file. Okay? So we're reading into a buffer that is not ours, right? Bad here. So we get we would get a page fault, but we would be in the kernel, wouldn't we? Because this is a system call. We can pass this address around all day long, right? We're just putting 32 bits in a register and putting it here and putting it on the stack, and it's like, put all those 32 bits wherever you want, just don't dereference them, okay? And so we go into the kernel, and the kernel says, you know what, before I write into that buffer that the user gave me, let me, just the off chance, let me just check if I can. And it'll check, and it'll find it can't. And so what will it do? Okay, so panic. Let's look at that as a possibility. What does panic do? Stops.
Stops the kernel. And this is something that the user did. So the user shouldn't get to stop the kernel.
Yeah. Now all of a sudden I've got a nice denial of service for you. We're sharing our x86 machine, and I say, I don't like Brad. I'm going to just go ahead and do a read on a bad address. Machine is dead. Not so good. So panic is not a great choice. It's another possibility.
You kill the process?
Yeah, kill the process. All right. So killing the process kills the process. So this is a possibility. For instance, you've got a toddler who, you know, this is really getting bleak. So you want to be careful of over-punishing, I guess is what I'm going to say. What would a milder punishment be?
Return an error?
Return an error. It's like, oh, you did something bad. This is much different from the case where you tried to access an address in your own user space, because there was no way for the kernel to talk to you and say you did something bad. Here, there's an easy way to talk to you. Return -1. You say, oh, -1, I did something bad. Or at least the read didn't work. My process didn't blow up. The machine didn't blow up. That's the least that you could do. So read will return -1.
In JAWS, don't we kill the process if you try to do this or something like this?
No, we have, back up a second. Do we?
Like I'm looking at my sys cputs and it has a user menacer that destroys the environment if your pointer is not.
It does seem extreme, doesn't it?
I don't know.
Yeah.
I think we could kill it.
So I guess we could go check and see. So read, sysread. So we have our pointer is the one that'll actually look and see you've got a pointer.
You don't kill it in x86.
Yes, we don't kill it in x86. Yeah, just seems like they would not have made it through parenting school. Okay, so the answer is yes.
If your child does something wrong, you just kill them. That way they can't do
Yeah.
anything wrong ever again.
Yeah. And what will finally cause us to stop executing?
Exit.
Exit. In x86, it's kind of interesting to see what happens if you don't put an exit. So in Linux, for example, when you compile your code and you have your main program, your code does not start at main. Your code starts at a small piece of code that calls main. And then when main returns, if it returns, calls exit itself. So if you've forgotten to provide an exit, they will provide one for you, basically. But that's not true for x86. And so therefore, you just fall off the end. Well, you fall off the end of main, and then where do you go?
Well, main's going to end with a return. So you're going to return to whatever happens to be on the stack.
Exactly. It's whatever, which was an empty stack, right?
So you're going to get a page fault.
You should probably get a page fault and die. Yeah, that's what should happen. All right. I don't know why it says question 3 continues. Push CLI. I redid the LaTeX, and so who knows what happened. Oh, I know what happened. I didn't re-LaTeX 3 times. So
There you go.
for those of you who are not LaTeX, just don't even worry about it. But so push CLI, so XV6 line 1667. So push CLI. Basically, push CLI will clear interrupts, right? And pop CLI will maybe turn interrupts back on. And so if we just replace this push CLI just with CLI, this wouldn't change much. at least as far as the interrupts were concerned. After you call this, interrupts are off. But this one would change in behavior, right? So sometimes in pop CLI, interrupts would still be off, and sometimes they'd be on, depending on our nesting level. So the behavior changes, that's true, but what goes wrong? Okay, so it's not just what would change. Well, they'd be different, because in one case, push CLI would do something different. Yes, but then what would happen? And so the key is, what would happen if you do a acquire a lock, right? So we acquire lock 1, acquire lock 2, release, I don't know, lock 2, and release lock 1. Right, and acquire turns off interrupts by calling push CLI, and release pop CLI. So in the before case, we're still locked here, right? But in the after, we're not locked at this place right here. So now what happens? So it's different, but what goes wrong? Okay. What goes wrong is, now that interrupts are on, certain things can start coming in, like interrupts, like give me an interrupt. Okay, reading for disk interrupt. So we go into the IDE, read write, I think, or something. We basically get into this interrupt handler, and let's say the interrupt handler wants to, so then we get an interrupt. And then the interrupt handler does an acquire on lock 1. Well, lock 1 has not been released yet. The interrupt handler is going to wait, spinning, until it becomes free, and it never is going to be, right? So we have a, I guess you could look at it as deadlock, sort of. But what goes wrong is the machine suddenly stops doing anything. Okay, that's what goes wrong. Because the way X86 is set up, the entire duration that you hold locks, interrupts are off, so that you don't have to worry about being swapped out, right? That's an entire critical section between when you acquire the first lock and you release the last lock. All right. Given a user-provided pointer to a buffer in user memory, like an argument to read system call, for example, explain what checks and translations the JOS kernel must do. So actually, this is slightly different. JOS doesn't even have a read system call, but you're providing some sort of a buffer. And the question is, what checks and translations must happen in order to read or write? What checks? I give you a buffer. I say, here, I am a user, to be trusted. Now you want to verify. What do you verify?
You want to see that the buffer is in the user space only.
You could check buffer in user space. So less than whatever the limit is. But there's some parts that even there they're not allowed to use, right? They're not allowed to use page. Yeah, we don't allow the 0 page. So a yeah.
You find the page table entry and you can check the permissions of things against each other.
Check permissions of associated PTEs. And I'm going to say E's plural because this buffer may span multiple pages. So what we're going to check is these permissions. And what are we going to check? We want PTEP, right? Yeah.
Doesn't it say the buffer is in user memory?
Yes?
Well, the user says it's in user memory. But
Well,
the users lie.
yeah, that's a... It's supposed to be a buffer in user memory, right? But JOS is still going to check, just on the off chance you got something wrong, right? It's going to check. So we check PTEP. We check PTE. What? Give me another character. U, and we maybe PTEW, right? Depending on whether we're trying to write to it.
Do we also need to check the page directory entries in case they're more restrictive?
Yes, really, we need to be doing the PDEs too. The fact that we write the PDEs, we can have written them to be permissive and therefore not check.
But I believe the user virtual page table, for specifically, we use the page directory entry to be restrictive because we can't change the page. We can't change the actual data. Am I wrong about that?
I remember something about that.
Like my vague recollection there is we use the page directory entry to set it as read-only for the user, because otherwise the user would be able to write to the entire page table.
I'll have to look at that. Yeah, it may be that one is a special case that we have not checked. It certainly wouldn't hurt to check the PDE, and we do that anyway in walk page dir. Don't we? No, because we just
return the page table
we do.
entries.
You're right. Yep.
I think currently.
Okay. Oh, and what translations do we need to do so that the kernel can actually write to the memory, if any? Do we need to translate from kernel to physical or physical to kernel? No. We're in user space. We're not running the kernel page directory. We're running the environments page directory. We have access to all that stuff. Do we have a mechanism equivalent to the switch? So the switch, right? So if we look at 3058, right? We're basically saving registers, switching stacks, and coming back in. So basically this is the coroutines where we have threading in the kernel, right? So this is handling, switch handles threading in the x86 kernel. And we switch between different kernel stacks, right? Where we have one per process plus one per CPU for the scheduler. Does JOS have all that many kernel stacks? How many kernel stacks does it have? One per CPU. So we have no need for any kernel stack swapping. There's no threading. The answer is no. Okay, does that make sense? We still have to save registers and restore registers, but that is not when we're switching between stuff in the kernel. It's instead when we are switching from kernel mode back to user mode. x86 enables interrupts. JOS doesn't have interrupts enabled while we're in the kernel. And so what if x86 disabled interrupts in the kernel? So there are long-running operations in x86, longer running than in JOS. So those would certainly delay interrupts. Okay, so we'd have a delay of interrupts. Because x86 has longer operations. But does that mean stuff just wouldn't work? Let's think about it. So it may be if we've got a fast peripheral that's sending data quite quickly that we're going to lose some data. That's a possibility. But will the operating system kind of be hobbling along, or is it just, I don't know, is it stuck in the kernel? So let's kind of imagine we're x86. Interrupts are off. So it's like, oh my gosh, this is nice. I can just run my thread, not worry about, other interrupts and stuff. And eventually, it's going to go schedule a thread to run, right? Or a thread to run, which is going to cause us to go back and run a process. While that process is running, interrupts are on, and stuff can be happening. We can be handling this I/O device that's generating stuff. Okay? As long as we go back to user space. But if we ever fail to go back to user space, what would cause us to fail to go back to user space? Or why would we choose not to is a better question. So why would we choose not to go run a process?
No processes are runnable.
Yeah, you only get to choose runnable processes. If no processes are runnable, then we don't want to run it. That isn't to say they might not be runnable in the future. So therefore, we're going to go to sleep, waiting for something to happen that'll change the state of these. But nothing will ever happen because interrupts are off. So we went to sleep, interrupts are off. We'll never wake up again. So the problem is, if there exist no runnable processes, right? This CPU sleeps, never to wake up.
Why don't we have this problem in JOS then?
In JOS, we re-enable interrupts before going to sleep.
So why can't we do
Or
that in
that
x86?
in x86?
Why? Say that again for JOS. Why?
The question is, in JOS we disable interrupts in the kernel, so why don't we have the same problem in JOS?
What happens in JOS? Let's just take a look.
And like, if we don't have the problem in JOS,
Yeah.
why can't we just do whatever we do there in x86? And then
Well, in XV6, right, our processes can be running, runnable, sleeping, waiting for what?
interrupt.
Yeah, I'm waiting for something. Do we have the same state in JOS? Let's see, where is this? In.h? So we have free, dying, runnable, running, and not runnable. And so not runnable is after an exo fork or something else. Let's look at one more thing. So where do we actually decide which environment to run again? That's in in.c, isn't it?
Well, actually, more to the point, in sketch.c, we have a part explicitly where if there's no processes to run, then we call sketch halt, and it re-enables interrupts before halting. So it seems like we could just
Yeah.
re-enable interrupts.
So here we are, yes. If there's nothing to run, then we give up, which is it's a much different approach than XV6 takes, right? And it sort of makes sense. If you have no, well, let me wait a second. So where is it we're turning on interrupts? Oh, for exercise 13. Yeah, we'll have to. I'll have to try and remember what will wake us up again. So I think I don't know what's going to wake us up again. So basically we're going to go into a halt state, stop running stuff on this processor, which will also save battery life, right? Save energy. And then something is going to have to wake us back up again, okay? Which is going to have to be some other CPU, which does that. So, but we'll get to that. Or the timer interrupt, because it could keep checking again and going back in. Yeah, that's a possibility too. So yeah, I guess you could have special code in x86 that does stuff like that, but it doesn't. And this is what would happen right now without any changes to x86. Yes, Brad?
So for x86, why is it that I/O interrupts can still occur?
I/O interrupts can still occur because whenever we go back to user space, interrupts are enabled. And so they can happen. So that'll cause us to jump back into the kernel and deal with that interrupt.
But what if we're sleeping, so like we go into the kernel and we sleep?
If we go in the kernel and sleep,
Yes.
sorry, in x86, if we go in the kernel and sleep, we'll run another process. If there are no processes to run, then we run into a problem. But as long as there is at least one process still to continue to able to run, we'll run it. And while it's running, interrupts can happen. Suppose you want to migrate of x86 so that a user process can address more than 2 gig of virtual memory. So currently, right, what we have is the user address space and the kernel address space. There's nothing about these address spaces that says anything about how much physical memory we have. Okay? We do map physical memory into the kernel. x86 is it? I always get x86 and JOS confused. x86 is kern base, yes, which is that 8? Yes, kern base. Is that kern base?
x86 has 2 gigabytes, whereas
Yeah.
JOS only has 256
Yeah.
gigabytes.
So we have physical memory mapped into here, right? So if we tried to move this user address space up, the way x86 is right now, we'd have to reduce the amount of physical memory that we could support, right? So we could have a 3 gig user address space, but then the kernel would only be able to access 1 gig of physical memory. There are still cases that could be useful to have a larger address space with less physical memory. You know, maybe what you're doing is paging in and out to disk. Why is it important that the physical memory be mapped in the address space? What use do we ever make of the fact that our physical memory is mapped into our kernel address space? Yeah.
The kernel uses it for things so that it has its own permissions to read directly from physical addresses.
How does it read directly from physical addresses?
Because they're mapped like.
Okay, so it takes it, it calls, what is it, kadder? Or am I remembering JOS? V to P or P to V. So it's going to call P to V, it'll map it in this address space, and then it can read it. It can find where it is in this address space, and then it can read and write to it, right? So kernel needs to read and write physical memory. Okay? And so it uses the mapping. But does the kernel need to always have that stuff mapped? No. So let's say we'll be generous. We'll go ahead and let it have all of its kernel code mapped. Okay? So its code is always there in physical memory. And we'll let its stack be in physical memory, and we'll let its data segment be in physical memory. But as it's working with other pages, like let's say you do a page alloc, and it wants to do a mem set to 0, that's a case where it needs to get a virtual address to be able to write zeros to it, right, to call mem set. Why couldn't it just go mess around with the page directory, set a mapping that it wants in the PTE, and then read and write from it, and then get rid of that? What if it had?
It doesn't even do
It doesn't do what?
Sorry, it doesn't use P to V to fill pages. Or to
Well,
fill pages currently.
yeah, so that's because it's already, yeah. So if you look at page alloc, it has what, the pages? Let's look at an example. So let's look at,
We only use to like address exotic types of memory.
Or fill in data structures that need the correct actual physical. Like there's places
Yeah.
where I remember we had to put them in.
Yeah, that's the other thing. Filling in references to memory that the CPU reads as physical
okay,
things.
so let me give you an example where it has to zero out memory, okay? If you do sbreak and allocate some pages, it's not okay for you to just get pages that the last process used, because that might have your SSH key that you guys have all set up. So, so it needs to zero it, right? In order to zero it, it needs to have it in its address space.
Yeah.
But it only needs it then. Once the user is using it, that's fine, right? So what we could have is a small, like a few, reserved pages in the kernel address space. All right. So we would change our picture to be user up here. And then here we'd have kernel code and stack and data. And then here we could have, I don't know, 2 pages. We'll just leave 2 pages. And whenever we need, because I'm imagining you might have to copy from one to another. That's why we'll splurge and have 2. So that any time that the kernel wants to read and write physical memory, it can map it into here. Do what it needs to do with it, unmap it. The concept makes sense? So all of a sudden, we could have our user address space be really big and also support an unlimited amount of physical memory at the cost of having to update these page tables and the associated cost of the cache, right? The PTE cache, yeah.
So kernbase would then, like in terms of the value of kernbase, it'll just make it larger?
Yeah, we would have to make it small enough so that all of our kernel code and data and so on can live in here, which is easy enough to do. Just find out how big that kernel is. Leave that there. Leave a bit extra for the other. Maybe we need to leave some for memory mapped I/O and some stuff like that, but that's basically it. Okay. Does that make sense? All right. I haven't yet put in the solutions some of the memorable errors or the best and worst parts. I need to actually summarize those. There were some difficult errors, for sure. And I know, yeah, I was working with Brad on one that was god-awful. I was working with Julius on one that, so the worst one, in my opinion, was the one I had in region ALEC back in lab 3, which in lab 4B came back to bite me. And it was, I think the same thing Julius and I had, basically fork tree was just dying after creating a couple children. And like we looked and we looked and we looked, and like the stack for the child was just getting zeroed out. Mysteriously. Well, it turns out if like you just never set your ref count on a page, someone else might use it and zero it out. And that was unpleasant. So you should be so happy you have GDB and are using an emulator as opposed to using real hardware, or even not a debugger, which can be real difficult. If you have questions about particular exam and how the scoring was graded, please feel free to see me, or you can also post requests on Gradescope.
Where is that?
Pardon me?
You mentioned like solutions to this being somewhere.
I will post it. I have it created. I just haven't posted it yet.
Also, there's a question on the Gradescope thing that is just adjust for midterm quantity of questions. What is that?
So that is, maybe you weren't here at the beginning when I said that I had a calibration error in the number of questions I provided was longer than I would have wanted. And so therefore this is a small increase to everyone's exam grade.
Okay.
So it counts as bonus points that doesn't affect the denominator of 75 points. Any other questions? Otherwise we'll break now. And two things. One, I'll wish you a happy spring break. But that assumes I won't see you, and I hope I do see you, or at least I'd be happy to see you in the lab. So I'll be in the cafe from 2:30 to 3:30, and then I'll be in the lab till about 7. So happy to help. Cafe first, and then the lab.